In this video, we're going to be discussing piecewise functions. We're going to be taking a look at how to evaluate them and also how to graph them. Okay, so first of all, the definition of a piecewise function. A piecewise function is a function that just combines different pieces of equations or graphs. So I have some examples listed there or shown there. So the first example we can see is three parts of three different linear functions. The blue part is an increasing function, the red part is a constant linear function, and the green part is kind of looks slightly curved there actually. So it might not be a linear function, it might be some type of curve for the green section. But for each piece, we have a different set of x values or a different domain. So for the blue part, we're seeing x values that are less than or equal to -1. For the red part, we're seeing x values between -1 and +1. And then for the green part, we're seeing x values that are greater than or equal to 1. So we only look at certain limited domains of each piece of the function. We could see piecewise functions written in function notation, and this is what they will look like. So this says f of x is equal to -x plus 2 when x is less than 0, and f of x is equal to 3x minus 3 if x is greater than 0. And then I have one more example of a piecewise function over here. Again, we have the red part, which is a constant linear function. This blue part we'll be learning a little bit later. This looks like a quadratic function, so it's a curved function. And then the green part is again a section of a linear function. So let's take a look at some piecewise functions that we're first going to evaluate. Okay, so I started with that very first example of the three parts of the graph that the first two at least look linear. This green part again looks like it could be curved slightly. But we're evaluating f of 2. So if we remember function notation, 2 is called the input of the function, or the x value is 2. And we want to evaluate that. So we want to know, well, what is the y function, or what is the y value? So when x is 2, I'm going to go 2 to the right. I need to figure out, well, what is that y value? And it intersects at a y value on that green function, and that y value would be 4. Okay, let's take a look at f of 0. Again, 0 is the input, so I know x equals 0, and we want to know, what does y equal? So when x is 0, I don't move left or right. I stay right there in the middle. So if I go up, the y value is located on the red line this time, and that's at a y value of 1. Lastly, if we want to evaluate f of -3, the input is -3, so x is -3. I'm going to move left 3 units and figure out where the blue line is intersecting. That y value is -1. So when we're evaluating piecewise functions, we're literally just seeing where the x and the y intersect the graph. In those last examples, we were given the input of the function, and we wanted to know the output, the y value. These ones are reversed. So we do not know the input. So x equals kind of blank, but we know the output of the function. So we know the y value in this case is -2. So to get to a y value, I'm going to move down 2 units, 1, 2, and again, see where the graph intersects and figure out what is that x value. So I'm in here on the blue function. When y is -2, the x value is -4. Okay, for the second example, again, we do not know the input. So we're finding x when the output is 0. So y equals 0. To get to a y value of 0, again, I'm not going to move up or down. I'm just going to stay put right at the origin. And again, that's still part of the blue function, but now the x value is -2. Okay, and the last example we do not know the input. So again, we're finding x when the output is 1. So the y value we know is 1. So if I go to where a y value is 1, I would move up on the graph. That is part of the red function. And we see that the x value is 0. I do not have to move left or right to get to it. Again, it's just staying at the origin. So x is 0. So we can evaluate piecewise functions, either finding x or y, and we see them written here in function notation, which is typical when we're dealing with piecewise functions. Okay, ladies and gentlemen, this next slide is a U-try. So I've switched the graphs out there, but you're doing the same thing we just did in the previous 2 slides. The first 4 examples, I give you the inputs. So I'm giving you X values, and I want you to find the Y values. And then for numbers 5, 6, and 7, I give you the outputs, and I want you to find the inputs. So find the X when you know the Y. All right, pause the video here and see if you can find those answers. Okay, hopefully you've had enough time to find those solutions. There are a couple that I'd like to talk about briefly. Number 3, if we take a look, the x value is 2. So if we move to where the x value is 2 on the graph, we see an open dot there on the green line. Remember, those open dots mean that you can get very, very close to that value, but you can never actually equal it. So there is no solution there, or we can see this symbol, the empty set. Okay, the next one I'd like to talk about is number 6. When we have a y value of 3, so we're going to go up 3 units, we see that there are actually 2 spots on the graph where the y value is 3. So I want to locate both of those x values. So that first one on the left side is x equals -1, and on the right side, x equals 1. So we actually have 2 answers for number 6. X could be -1 or x could be +1. Okay, this next example, we're still evaluating piecewise functions. However, instead of being given a graph, we're given an equation in function notation. Rather, 2 equations in function notation. So let's take a look at our first example. It's asking us to evaluate for an input of 2. Again, that tells me the x value, so I know x equals 2. Well, in order to evaluate this function, I need to know what piece I'm supposed to be looking at. So this is where the domain is going to come into play. So if x equals 2, I need to figure out, should I be looking at this first function, -x plus 2? But that's only valid when we have a domain that's less than 0, and 2 is not less than 0. We would be looking at this function, 3x minus 3, if x is greater than 0. And if you notice, x equals 2, x is greater than 0. So I'm actually looking at this second function when I go to evaluate, and I'm kind of ignoring the first one because it's not in the correct domain. So I'm going to plug a value of 2 in for x. That would say 3 times the x value of 2 minus 3. 3 times 2 is 6, and 6 minus 3 gives us 3. So when we have an input of 2, we would have an output or a y value of 3. Okay, I'm going to switch colors for this next example. So this next example is going to be in blue. It's asking us to evaluate f of -4. So again, I need to see, well, what domain does that fall under? Is it x is less than 0 or x is greater than 0? -4, hopefully it's clear, that x is less than 0. So I'm going to be looking at this top equation and again evaluating for when x equals -4. So if I plug -4 in for x, be careful of signs, the opposite of x, so that's the opposite of -4 plus 2. Well, the opposite of -4 would be +4. Plus 2 gives me 6. So when x equals -4, the output or the y value is 6. Let's do one more together. I'm going to erase some of my circles up above since those first two examples are kind of in the way. Here we go. I'm going to switch colors and I'm going to use orange for this one. We're finding an x value of 1. Well, we're finding the y value when the x value is 1. If I take a look at the domains, again, I need to determine, is x less than 0? No. Is x greater than 0? Yes. 1 is greater than 0. So I'm back using that bottom equation. The x again is 1. So if we plug that in, 3 times 1 minus 3. Well, 3 times 1 is 3, minus 3 gives us a y value of 0. So when x is 1, the y value is 0. All right, pause the video here. Try those last two on your own, and then unpause the video to get those solutions. Okay, hopefully you've had enough time to take a look at those. Number 4 asked us to evaluate when x is equal to -2. That is in the domain x is less than 0. So I used that first equation and got a y value of 4. On the second one, we have to evaluate when x equals 0. X is not less than 0 and x is not greater than 0. So there is no function that I can plug this 0 into and get a y value out. There would be an open dot at an x value of 0. So we have no solution or the empty set. Just like when we were evaluating using a graph, we could be given the y value and asked to find the x value. So these next couple of examples are going to go over how to do that. So for this first example, we're asked to find x, so we do not know what x equals, but we know the output of the function, or the y value, is 0. So what we're going to do is we are going to plug that into both of these functions and see which one is the solution. So let's take a look at the top function. It says -x plus 2, and we want that again to give us an output of 0. Solving this equation, we're going to subtract 2 from both sides and get -x, or the opposite of x, is equal to -2, and divide both sides by -1. So we get x equals 2. Now, before we just accept this as the solution, I need to look at my domain for that top function. It says that that's true for when x is less than 0. So my solution, x equals 2, is that less than 0? No, it is not. So that is not my solution. That's called an extraneous solution. It's not part of the domain that we wanted. Okay, so let's take a look at the second function. It says 3x minus 3, and again, we want the output to be 0. So if we add 3 to both sides, we get 3x is equal to 3, and dividing both sides by 3, we get x equals 1. Taking a look at the domain, it says if x is greater than 0. If x is greater than 0. Let's take a look. Is our x greater than 0? It sure is. X equals 1. That is greater than 0. So that is my solution. So when y equals 0, the x value is 1. Let's take a look at another one of those. Okay, this example, again, we're finding x. So we want to know, what does x equal if the output is 3, or in other words, the y value is 3. All right, let's substitute it into that first equation. So negative x plus 2 is supposed to equal 3. Solving that, we're going to subtract 2 from both sides. We get negative x is equal to 1. And dividing both sides by negative 1, we get x equals negative 1. Checking the domain, it says that that's true if x is less than 0. So, is our x value less than 0? Yes, it is. So I'm going to box that. Let's check the other equation. So we have 3x minus 3 is supposed to equal the output value of 3. We would add 3 to both sides. So 3x equals 6. And dividing both sides by 3, we get x equals 2. Checking the domain, x is greater than 0. Is our x value greater than 0? Yes, it is. So we actually have two solutions to this problem. We have two x values, negative 1 and positive 2, that give me a y value of 3. Okay, this next slide is a you try. I would like you guys to find x when the output, the y value, is negative 3. Pause the video here and then unpause to see if you're correct. Okay, for that equation, I plugged the first function, negative x plus 2, and set it equal to negative 3. When I solved that, I got x equals 5, but checking the domain, x has to be less than 0, which 5 is not less than 0. The second function, 3x minus 3, again setting that equal to negative 3 and solving, I got x equals 0 for that one. Checking the domain, x has to be greater than 0. Well, 0 is not greater than 0, so we had to throw that one out too. There is no solution. This is the empty set. Okay, the last portion of our notes today is going to be talking about how we graph piecewise function. So given our function up here, it's the one that we've been dealing with evaluating in the past couple slides, we're going to go ahead and graph that function so we get a visual of what it's looking like. So a couple different ways that you can do this. I'm going to show one method on this particular example and a different method on the next example. So you can pick and choose what works best for you. So we've talked a lot about how to graph linear functions. So let's just take a look at this first equation. It says y equals negative x plus 2. So if we were graphing the whole entire equation, let's go ahead and get a graph started of what that's going to look like. We're going to have a y-intercept at positive 2. Since our slope is negative 1, I'm going to move down 1 and right 1. I'm going to put a little bit, a couple extra points on here. So hopefully I can make a straight line. Okay, but just like when we talked about graphing with limited domains, we actually don't want the whole entire line. So we just want the x values that are less than 0. So remember, an x value of 0 is going to be the origin. So if I want the values that are less than that, left is always less. So I want the values to the left of 0. So I need to erase anything that's to the right of 0. Okay, and one more thing that I need to think about. Because this said x is less than, I actually do not want to include this point at 0. So there's going to be an open dot at that 0, 2 coordinate. Okay, I'm going to switch colors and let's go ahead and take a look at the second function. Y equals 3x minus 3. And actually, I think I'm going to put that in red instead of blue because my graph is blue. So let me just circle that in red. So my y-intercept is at -3. So I'm marking a point at -3. And my slope is 3. So I'm going to go up 3 and over 1. Okay, if I go ahead and connect those points in a straight line, there is the whole entire graph. However, I do not want the whole entire graph. So if I limit the domain to just x values that are greater than 0, greater than 0 means to the right of an x value of 0. So again, I'm at the origin and I want to use only the part of the graph that is to the right of that. So I'm going to erase anything that's to the left of an x value of 0. Again, thinking about x has to be greater than 0, I'm going to again put that open dot at the coordinate 0, -3. Because again, I want to get very, very close to an x value of 0, but I actually do not want to touch it. So we can see that this piecewise function consists of two linear functions, the purple part and the red part. All right, on the last example, I showed how to graph the entire line, and then you erase the parts that you actually don't want to include in the graph by looking at that domain. I'm going to show a slightly different method for how you can come up with those values using more of function notation and substituting in x values that you want. So for the first part, our first function says f of x is equal to x plus 5 when x is less than -2. So let's first put in the value of -2. So if I plug in -2 in for x, that would say -2 plus 5. Well, -2 plus 5 gives me a y value of 3. So when x is -2, the y value is 3. But I would have an open dot there because, again, x has to be less than -2. So I'm going to put an open dot at that coordinate. -2 was x, and the y value that I got out was 3. Okay, if x has to be less than -2, I could pick anything to the left here. So I'm going to pick the value -5. So if I plug -5 in for x, -5 plus 5 gives me 0. So when I picked -5 for x, I get 0 out. So I'm going to put a dot at -5, 0. I could continue to pick points, but in order to write a linear function, I really only need 2 points. So I'm going to connect those points and indicate that I'm going to keep going in that same direction when the x values are getting less. Okay, I'm going to switch colors and take a look at the next function. We have -2x minus 1 when the x values are greater than or equal to -2. So again, I'm going to start with -2. If we plug -2 in for x, -2 times -2 minus 1, well, -2 times -2 would give me +4, and +4 minus 1 would give me 3. So when we put -2 in for x, we get 3 out. Notice that this is x is greater than or equal to -2. So this time, -2, 3 is going to fill in that open dot with a closed dot for the blue line. Okay, it's very hard to fill in that whole dot, so hopefully we're understanding that I'm filling in that open dot with the blue. Okay, x has to be greater than or equal to 2, so I can pick anything greater than or equal to -2. I already picked -2, so let's pick a number that's greater than -2. Let's say, for instance, 4. If I plug 4 in for x, -2 times 4 plus, oops, I'm sorry, -1 is what that equation would read. And if we do that math, -2 times 4 gives me -8, -1 gives me -9. Woo, good thing I didn't pick anything greater than 4 because I would be off the graph at this point. So my x value that I picked was 4, and we got -9 out. So let's mark that point on the graph. 4, -9. Again, I really only need 2 points to connect them. So I'm going to connect those 2 points and indicate that I'm going to continue on in the positive direction for x. There is the piecewise function. Okay, this last example is a U-try. So pause the video here, see if you can complete that graph of that piecewise function, and unpause to get the solution. Okay, here is the solution to that graph. You can see the y equals 2x plus 1, or f of x is equal to 2x plus 1 when x is greater than or equal to 1. It's the pink portion of the graph. And then f of x is equal to 1/2 x minus 3 when x is less than 1 is the purple part. This value, when x equals 1, it is at a y value of -2.5, and we want to make sure that that's an open dot there. Okay, this concludes the notes on piecewise functions.